Hello students, welcome to video lecturing class. So today we will discuss about the gyroscope. So this is the second bit in the third model. Already studied governors. So we'll start with the gyroscope. Basically it is an instrument and acts as an processing intelligence. So this is the instrument which is doing the gyroscope. So here you can see this is the x-axis and y-axis, and this is the rotor. So in this figure, if the rotor is spinning about x-axis and any attempt is made to move any one of its part, that time it will resist the motion. That means whenever you want to change the direction, okay, so this gyroscope effect will come into picture. Therefore, when it resists the motion, it confirms the laws of statistical equilibrium and of gravitation. The important application of gyroscopic principles are to guide the missile, to control the aeroplanes, stabilizing the ships, and in space travel. So moving further, so let us try to define some of the terms. So first one is gyroscopic effect. So when a body is rotating about an axis of symmetry, it offers resistance to change in the direction of this axis. So this effect is known as gyroscopic effect. The next one is linear momentum. It is defined as the vector which has the same direction and sense as that of velocity, and its magnitude is the product of the mass and magnitude of the velocity of the vector. Then the next one is angular momentum. It is defined as the moment of linear momentum. For example, if a particle of mass m rotating with the angular velocity omega and radius r, then we can write the angular momentum vector as mvr, which is given by m into, that is mass, into omega into r, that is velocity, angular velocity, into r, that is radius. So it gives you m r square into omega, which is equal to I into omega. Now we will try to define, or we will try to write the equation for gyroscopic couple. So let us consider a disc which is keyed to a shaft. It is rotating in the bearings x and y as shown here. Okay. The axis about which the body rotates is called as axis of spin, and the axis about which the axis of spin tends to turn is called as axis of precision. This is axis of precision and this is axis of spin. So this is the axis about which the body is trying to rotate, and axis of precision means if your axis of spin is tending towards this axis, then we can call it as axis of precision. The axis about which the torque is present is known as torque axis. That is this axis. And the axis S, P, T are mutually perpendicular to each other. That is, this is S means axis of spin, P means axis of precision, and T means axis of torque. So these three are mutually perpendicular to each other. Now we can write the angular momentum equation. The angular momentum is given by I into omega, and by right hand rule, the angular momentum vector, that is h, is directed downward. Here shown in the figure, it is directed downward. So the shaft is tilted or displaced through an angle delta theta about the axis p. The angular moment changes from h to h dash, and then delta h is the change in angular momentum. So here initially it was h, then now it is h dash. So by changing h to h dash, then it is delta h. So to determine delta h, we need to draw an arc by taking O as the center point. Let's take this O as center point, A as radius, draw an arc. Then we will get arc AB equal to OA into delta theta, where we will give you the I into omega into delta theta, because this OA is nothing but I. As delta theta is very small, we can write as arc AB is equal to chord AB. So now the chord AB is given by delta H, which is equal to I into omega into delta theta, that is change in angular momentum. Therefore, the rate of change of angular momentum, that is dH by dt, is given by limit delta t tends to 0, I into omega into delta theta divided by delta t. When you apply the limits, it will give you I into omega into d theta by dt, which is equal to I into omega p. So here we define one more term, that is omega p, this precision velocity. And you can write the gyroscopic torque, equation for the gyroscopic torque or gyroscopic couple is given by G equal to I into omega p. Also we can write the gyroscopic couple equation as G equal to F into L, where this F is force exerted by bearing over the shaft and L is distance between two bearings. Now moving further, I will try to study the gyroscopic effect on aeroplane. So first we will consider the case number 1. So here let us assume that propeller turns clockwise when viewed from the rear, that is from the tail end, and the aeroplane takes the left turn. So here the propeller is rotating in clockwise and the direction of weaving is from the tail. So in this figure, this is the axis of precision and this is the axis of spin. And the aeroplane is now, here it is taking left turn. Okay. So the angular momentum you can represent it by the vector diagram here. That is OX is before turning. This OX is before turning. Its direction is obtained by right hand thumb rule. Okay. And along the axis of the spin, the thumb will indicate the direction of vector OX. Therefore, the angular momentum after turning is shown by this OY. This is after turning. Actually, it was OX. Okay. So after the effect, it changed to O into OY. Okay. And in the same figure, I have shown this X dash and Y dash. So here Y dash to X dash is the reactive couple and is perpendicular to OX. So this couple acts in vertical plane and it tends to raise the nose and dip the tail of the aeroplane. So the initial condition was propeller is turning in clockwise direction when viewed from the tail, that is from the rear, and the aeroplane is taking a left turn. So that time the effect will be it will raise the nose and dip the tail. Second case, assume that propeller turns clockwise when viewed from the rear and the aeroplane is taking right turn. So here the direction of rotation is same, but the only thing is aeroplane is taking right turn. So that time the angular momentum is represented here. Ox is the angular momentum vector before turning and its direction is obtained by again right hand thumb rule. So Oy is the perpendicular angular momentum after turning and Xy is the applied or active gyro couple and this X dash Y dash is the reactive gyro couple. So effect of this couple is it will act in the vertical plane and it tends to dip the nose and raise the tail. So the effect will be, it will dip the nose and raise the tail. But in the first case, where it is to raise the nose and dip the tail when it is taking left turn, but when it is taking right turn, that time it will dip the nose and raise the tail. Now moving further. So assume that the propeller turns counterclockwise when viewed from the rear, that is from the tail end, and the aeroplane takes left turn. So all the conditions are same, only thing is the direction of propeller, rotation, direction of motion of propeller is, this time it is counterclockwise, and when we are viewing from the rear end, that time the aeroplane is taking left turn. So the angular momentum can be obtained by this vector diagram. So this is O to X is before turning. Once it will take the turn, that time it is represented by O to Y. So this X to Y is active gyrocouple and this X dash to Y dash is reactive gyrocouple. So the effect will be, it will tend to dip the nose and raise the tail. Next, fourth case is propeller, when the propeller turns counterclockwise when viewed from the rear and aeroplane takes the right turn. So again, by drawing this vector diagram, you can get the angular momentum. So this O to X is before and O to Y is after, and this XY is the active gyro and X dash Y dash is the reactive gyro. So here the only difference between first two and this third and fourth is the propeller direction of propeller. Okay, so there it was clockwise and here it is counterclockwise. So just you need to reverse the conditions while defining this, while drawing this vector diagram for the angular momentum. So the effect will be, it will tend to raise the nose and dip the tail. Now the fifth case, propeller turns clockwise when viewed from the rear end and the aeroplane takes off, or making the nose to move upward in the vertical loop. So in previous cases was about to taking the direction turn about left and right. But in this case is for the takeoff of the aeroplane. So again, when you are looking from the rear end, the direction of the propeller is clockwise and the aeroplane is taking off. So that time what will be the effect? So that effect we will come to know after drawing this angular momentum vector diagram. So here this O to X is before turning or before takeoff and O to Y is after takeoff, and this direction is for the active gyro and this direction is for, that is X dash Y dash is for the reactive gyrocouple effect. The effect will be, this couple acts in the horizontal plane and tends to turn the nose towards right side when the aeroplane is taking off, and if the propeller is rotating in clockwise direction when you view from the tail end, that time the nose will tend towards right side. Then fifth case is propeller turns clockwise, again that condition is same. When viewed from the rear end, the aeroplane is landing. So the fifth case was for takeoff, now it is for landing or making nose move downwards in vertical loop. So here this O to X is before landing and O to Y is after landing, and this is the active gyro and this is the reactive gyro. So in this case the couple will act in horizontal plane and it tends to nose towards left side. While landing it will tend that nose towards left side, and while takeoff towards right side. That is when the plane is the propeller is having clockwise direction, propeller is rotating in clockwise direction when viewed from the rear end. Then the seventh one is propeller turns in counterclockwise direction when viewed from the tail end and the aeroplane takes off. The nose move upward in vertical loop. So if you observe or if you compare this vector diagram for the takeoff of the aeroplane when you for the clockwise and counterclockwise, just you need to reverse the effects. Okay. So here this couple acts in horizontal plane and turn the nose towards left side. Similarly, the eighth case is when the propeller is having counterclockwise when viewed from the rear end and the aeroplane is landing or making the nose move downward in vertical loop. So this is for the landing case when the propeller is turning in clockwise direction, counterclockwise direction. So here this O to X is before landing and O to Y is after landing, and this direction is for the active gyro, this direction is for reactive gyro. So here this couple will also act in horizontal plane and it tends to turn the nose towards right side. So in first 4 cases the couple is acting in vertical plane, in this last 4 cases the couple is acting in horizontal plane. So in all 8 cases the gyroscopic couple, that is G, is given by G equal to I into omega p, where this I is m into k square and omega is given by 2 pi m by 60. Omega p is given by v by r, where this v is speed of the flight in meter per second, r is the radius of curve, and k is the radius of gyration of the propeller in meter, and I is the mass moment of inertia in kg meter square, and m is mass of the propeller in kg. Okay. So here the only thing is need to remember, need to understand the direction of the propeller and the direction of the observer, that is in which direction you are moving the plane. That is, here if you take this case, the propeller turns counterclockwise when viewed from the rear end. When you are viewing from the rear end, that time the propeller is rotating in counterclockwise direction. For the same case, if you are viewing from the front, that time the propeller will be rotating in clockwise direction. Okay, so keep constant this direction of viewing, that is always you try to view from the rear end, so that you can easily understand the effect of the gyroscopic couple on the directions. That is, if it is having the right turn or left turn, or if the plane is take off, or if it is landing, that time it will be very easy to draw this angular moment vector diagram. Okay. So in the next class we will try to solve some of the simple problems on this gyroscopic couple. Okay, thank you.